Okay, now we're live. We can start.
We are live. Okay. It's a pleasure to introduce Alejandro Cabrera from Universidade Federal do Rio de Janeiro, who will talk about everything you want to know about semiclassical quantization of Poisson structures. So this is local symplectic groupoid generating functions on the Poisson sigma model. And you couldn't write because there were too many information on the slide.
Okay. First of all, thanks for the invitation to the organizers for this very nice initiative to have the global seminar on Poisson geometry. So I will go directly to the talk. The structure of the talk will be like this. There will be introduction and basic definitions. Then I will mention some results, and I will do some quick final comments at the end. So the first, I will mention some introductory remarks. I kind of look at this map and try to accommodate all the things that I'm going to say in this map. So the first results will be about Poisson geometry, let's say in itself. The definitions belong to here and the techniques belong to here. Then there will be another result which kind of relates this to quantization. And then a third one that relates this to field theory. And this will somehow commute with some known relations between these two fields. I want to also explain quickly some of the things that appear in the title. The semi-classical part makes reference to the fact that we will not be addressing the full quantization. For example, if there is a quantization formula, it will only be an extract that we will be dealing with. And the same happens here. Then another thing is this non-perturbative aspect, meaning that the results here and here will not involve formal power series, but actual or ordinary functions. And then it's only when we do Taylor expansion that we will recover some formal objects. I will remember this diagram. I hope you can remember the P is Poisson, Q is quantization, and F is fields. And I will be highlighting where we are along the way. Oh, sorry. I meant to put great. So going a bit more into detail, I want to present this key relation. You can find more details about this in a paper of Cattaneo Deranfelder that I will mention many times today. Oh, sorry. Oh.
You stopped sharing for some reason.
Oh, sorry. Yeah. I will restart sharing. How do I do that?
Share.
Sorry, yeah.
Okay. Below.
Yes, this one. Is it
Excellent.
okay now?
Yes.
It's only that this is a bit annoying. The stop share, it's exactly on top of the colors. Can I move them? Okay.
Maybe you can make it smaller.
Yes, that's a good idea. Do you see this well?
Yeah.
Oh, sorry.
It changes. Everything.
Okay, now it's doable. Okay, we're back. So there was this key relation. on this side, this is a star product, which is a family of products that is meant to quantize an underlying Poisson structure that appears in first order in this parameter H. And in this kind of key relation that one could assume that it holds, it appears this exponent here. So when h is goes to 0, this is a fast oscillatory exponent, and this is typically referred to as being the semiclassical contribution, because it's the leading term in such an expression when h goes to 0. And the connection between the things that I'm going to say can be seen in this formula like this, that the fact that this is associative poses some special properties on this function S. And this can be reduced to the fact that this is a generating function.
Excuse me, what is P1 and P2?
Sorry?
Excuse me, what is P1 and P2? They're supposed to be just momentum variables?
Yes, they are, if you want, they are Fourier-like variables, but I will mention this in a second more. Yes, but that's what they are.
So you probably have some linear functions, so it's not just P1.
These P1 and P2 are seen as linear functions, yes.
Yeah, okay.
Thank you. And yeah, then what you see is that the condition on this object is that it's a generating function for something called local symplectic groupoid that I will introduce next. But before doing that, let me just show you a couple of formulas without addressing them yet. We will be thinking of a very particular star product, which is Kontsevich star product in this coordinate Poisson coordinate manifold. And we will also, in the third part, we will be substituting this explicit formal power series by this field theoretic expression. So that's essentially the plan of what we are going to speak about. Okay, so let me go quickly about two basic definitions. So we are here in this Poisson geometry world, and I will be recalling definitions. I hope the audience is more or less familiar with them. So first of all, about groupoids, one way that I have to think of this is by analogy with groups. For groups, one incarnation is transformations of spaces. But for groupoids, at least in this talk, it's useful to think of transformations of individual points separately, not of the whole space. And so then the groupoid structure, there is a set of arrows, a set of objects, and there are structure maps. For example, the source of the arrow, the target, there is an identity arrow for each object, there is an inversion, and there is a composition like this. In the context of Poisson geometry that we will be dealing with, there is a Lie theoretic way of addressing the resulting groupoid structure like this. We first think of infinitesimal arrows as given by covectors in M. I'm doing this in coordinates, but it could be done invariantly, just for simplicity. And the idea is that if you take such an infinitesimal arrow and you want to produce a finite arrow, one way of doing it is by solving this differential equation. And you understand, in this picture, you understand the arrow as being formed by the parameters that entered the equation. For example, the initial point and the parameter P. Or you could also equivalently take the endpoint or some middle point, and this would all give you equivalent descriptions of some underlying groupoid. Let me quickly also mention two words. So Lie makes reference to the fact that the space of arrows and objects are both manifolds, and all the structure maps are considered to be smooth. And this local part, it's a bit less familiar, but maybe people are more familiar with local groups, local groups or locally groups. And the idea is that here we only require the structure maps to be defined only near the units. So in this picture that I was saying, the idea is that we only have a groupoid structure maps only for small parameters P. So just to give you a flavor of how this works, composition is not defined for all composable arrows, but just on an open subset that contains these composable identities. And the size of this open neighborhood is not relevant for us. So one way, a formal way of addressing this is that we will be focusing on the germ of the structure. So the final simple ingredient is this, I forgot to say, I'm going to show you examples now. So if you're not completely following, don't worry. I hope the examples will clarify this. The symplectic aspect of these local groupoids goes like this. We think that the space of arrows comes with a symplectic structure in such a way that the relation that gives the composition, so A, B, and the composition of the two living inside here is Lagrangian. There are these two minus signs, which are important. And this can be seen to be equivalent to a cocycle condition on these two forms. So patching all this together, something that I want to recall from this is the following. If you have one such local Lie groupoid, which is symplectic, one can show that there exists a unique Poisson structure on the space of objects. And the condition to define this is that the source map is a Poisson map. And when this happens, so when the Poisson structure is induced by such a local groupoid, we say that this G integrates the Poisson manifold. So this is an analog of integration of Lie algebras to Lie group, and actually generalizes it, as we will see in a second. So, okay, some examples quickly. If the Poisson structure is 0, we can give a very simple integration because we don't have to make anything finite. The infinitesimal picture already serves. So arrows are covectors seen as going from X to X, and the composition is just addition. The symplectic structure is canonical. And if you want a truly local symplectic groupoid, you could restrict the structure to a neighborhood of the 0 section. Here, 0 is what the identity arrow. Now, if the Poisson structure was symplectic in the other extreme end, we can provide an integration based on pairs. So the arrows are just pairs, and composition of arrows is given by this kind of transitivity condition. The symplectic structure is this pair with this minus sign, which makes the diagonal Lagrangian. The identity is given by the diagonal pair. And if you want a truly local symplectic groupoid, you can restrict all the structure to a neighborhood of the diagonal. And finally, suppose that we are in a vector space, that I think of it as dual of something, and that the Poisson tensor depends linearly on the point where you are. Then you can check that these objects define the structure constants of a Lie algebra that I call H. And we can provide an integration of the Poisson structure by using an integration of the Lie algebra. So I take a group, a Lie group that integrates the Lie algebra, and I take its cotangent. So notice that in the first example above, we were considering covectors in M, and now we have covectors in a different thing, which is the Lie group. But the structure is written up here. The idea is to use the multiplication, the group multiplication in H, to move the covectors around to the appropriate places. And if you truly want a local picture, here I trivialized the cotangent bundle as a product like this. I won't touch this factor, the linear factor, but I do restrict to a neighborhood of the identity in the group as is depicted here. And this is what gives you the local symplectic group. So I hope these examples more or less illustrate what I was saying. Let me mention some structural results about this. So every Poisson manifold admits such a local integration. This is in particular in a paper of Kost, Dazord, and Weinstein. When the Poisson manifold is a coordinate space, which will be an important case for us to compare to quantization formulas, there is a very particular construction that comes from the work of Karasev, and I will be calling it Karasev integration. So it's given by very explicit smooth maps defined on R2N or neighborhoods, open subsets of R2N. I will mention the explicit formulas in a second, but for now, I just want to keep this idea that in the coordinate space, we have an explicit integration. And another question is that you can think of the problem trying to extend this local structure to a, let's say, global, so that you can always multiply any arrows whenever they are composable. And this is known that it's not always the case. The theory of obstructions behind this global problem was developed by Kreinig and Fernandez. And there is also an alternative approach, which is newer by Fernandez and Michelis, that is based on local groupoids. I will maybe mention this at the end again. So I hope this is a more or less clear picture. We have these local symplectic groupoids, and in a very precise sense, they integrate the Poisson bracket. So they give like finite transformations corresponding to, let's say, Hamiltonian vector fields, for example. So now the final ingredient is this thing that I was mentioning, and this is the true, let's say, new focus of this talk, generating functions. So what is the idea here? The idea is borrowed from symplectic geometry. Remember that in our groupoid, the Lagrangian, the graph of multiplication was a Lagrangian relation. So there is a Lagrangian submanifold here. And the idea is to try to encode this Lagrangian with a function so that it's an exact Lagrangian. To do this, we use another piece of data, which is, I would call it a framing. So we have some cotangent bundle, and we think of a, oh, this shouldn't be red. Anyway, maybe I'll just turn it blue. Good. This neighborhood of the zero section into some Lagrangian, reference Lagrangian here, and some neighborhood. And the idea is that when we map back this red Lagrangian, it will be something here in the cotangent bundle. And what we want is that it's given by the graph of this, the differential of a function. So Z goes to dZs. So at each point of X, we have a covector sitting on top of it. So this is the idea of the generating functions. I repeat, the graph of multiplication becomes an exact Lagrangian in this frame. The pair, I call it generating function data. And okay, this is a very general kind of notion. Let me show you the type of functions that appear in this way. And for that, I come back to our coordinate special case. In this coordinate manifold, there is a particular reference frame that you can use that I call nus C. And with respect to that, for example, you can integrate a constant Poisson structure just by this very simple formula. There is a linear part that contains the addition of covectors, and then there is a quadratic part that contains how this is being modified by the Poisson structure. When the Poisson structure is non-constant, you will need, in a sense, more terms here that will depend on the derivatives. For example, if the Poisson structure is linear, so it corresponds by duality to a Lie algebra, the formula that appears is this. Here is the Baker-Campbell-Hausdorff series in these two parameters, P and P1 and P2, which naturally live in the Lie algebra. And then it's paired with X, which lives in the dual. But you see, this is a non-trivial function compared to this one. In general, you can think of an arbitrary Poisson structure smooth, and you will expect something that contains all sorts of derivatives of pi. So the first result addresses that point. Now we are in this map, we are going to see a result about these Poisson geometric objects. The first part, I condensed this in a theorem. The first part says that any local symplectic groupoid admits such a framing with special properties that I will mention afterwards. The second part is that for each choice of such adapted framing, there is a unique germ of generating function corresponding to it. So once you fix the framing, then you get a generating function, and a normalization condition for it is given by its vanishing on the units, just to kill ambiguity by adding constants and so on. And a third part, it makes reference to the coordinate case. Remember that the coordinates case is special for us because it's the one where we are able to compare with the explicit formulas coming from quantization. So here we have this coordinate Poisson manifold. So first of all, there exists a natural framing just using the coordinates. And this happens to be adapted to this explicit Karasev integration. And because of this point here, we know that there is a generating function. But the key point of this thing is that it's given by explicit formulas. Let me show you these formulas quickly. The idea is not for you to absorb all the complexity, but let me mention just a couple of things. For example, so what is this? This is an Euler vector field that rescales the P1 and P2. Alpha and beta are maps that I'm going to define right now. And this is a Hamiltonian flow. In R2N. With respect to the canonical symplectic structure. So this is from the perspective that I was mentioning in the examples, this is a very nice formula because by using these flows and this integral, you are able to encode all the possible complexity that appears when the Poisson structure is nonlinear. So let me give you just one more detail. This is the source map or symplectic realization map that Karasev introduced, is defined implicitly by this condition. So by using implicit function theorem, you show that this actually defines a smooth function alpha pi. And this phi here, which is different from this one, it's exactly the flow that I mentioned in the beginning, which turns infinitesimal arrows into finite arrows. So this is what appears here. The beta map, which is the target, is just flipping the sign of the P. This happens because the inversion is actually given by multiplying by -1, as happens in the Baker-Campbell-Hausdorff local structure. And there is another flow here that relates the X and the X0 that appears here. So altogether, this is a system of concrete equations that define implicitly this function S. If you restrict to the particular cases that I mentioned before, constant and linear, you recover actually these two formulas but it also works for an arbitrary Poisson structure. So, okay, this is the first result. Let me give you just a couple of details so that it's not obscure what this adapted thing means. It's a very mild condition. It means that this reference frame contains the units, so the points that are like this, unit, unit, unit. And the reference manifold X that we use is an open subset here. So these are pairs of covectors that share the same base point. And this is an open that contains 0. The idea being that 0, this 0x, 0x is being mapped to these triple identities. And there is also a further infinitesimal condition on the symplectic normal directions that I'm writing, but it's the natural, it's a natural normal form near the units. And finally, I mentioned that in the theorem, it says germ, and it's always germs around these points in X. So one more thing, the steps in the proof, as I said, they're very typical steps in the context of symplectic geometry, actually. So you use transversality, for example, to show that this red Lagrangian now in the frame, it's horizontal. So it's given by the graph of a closed one form. And then you use rescaling properties in these two covectors to find the potential for it. Okay, I hope so far so good. So let's move to the second part. So in this part, we will use this knowledge that we have here about these local groupoids and their generating functions. So I just wanted to check that everybody is listening. So we are going to use this knowledge that we have on this Poisson geometry side to relate it to this part of quantization. So what I'm going to do next is a bit untidy, but I hope it will be illustrative. So on this right side, it's a formal family of functions of P1, P2, and X as they were appearing before, but now we also have a formal parameter. So this formal family of functions was introduced by Cattaneo, Duran, and Felder as an extract of Koncevich's quantization formula that I'm going to explain in a second, in which sense it's an extract. And they showed that this particular extract of Koncevich's quantization formula actually defines a formal family. So here, formal is because it depends on this epsilon parameter of symplectic groupoids. So they knew this, of course, they knew these connections that I was mentioning in the beginning quite well, and they provided this explicit formula for such a generating function. The difference between this and the result that I just showed before is that this is a formal series, and before it was a non-formal series, and it was actually much simpler. It was one integral. So anyway, let me tell you, so Koncevich's formula looked like this, the black letters. To get to the formula that they provided, first we change f times g by p1 plus p2. You can think that you are looking at the logarithm of this when these are exponentials. Another thing is that we change the name of the formal parameter from h to epsilon. This is, in a sense, might sound silly, but it's conceptually important. Then another thing, instead of summing over all these Koncevich graphs, we sum only over those which are trees. So they contain no loops and they are connected. And we also changed this by the symbol of this bidifferential operator. So now the symbol depends on P1 for the derivatives on the first argument, P2 for the derivatives on the second, and X, the point where you are. So given this definition, the second result is this, that if we do the non-formal construction that I was mentioning in the first result, and you take a formal Taylor expansion, so around t equals 0, so it's 0 plus epsilon, then you recover exactly this one. So this formula that I showed you with an integral condensates all this complexity with graphs and weights here. So they are the same formal power series. And there is something more that I accumulate in this result that, let me say it in a few words. If you didn't know the formula for this, you could actually guess it or derive it, deduce it from the analytic formula. And to get from these integrals to graphs as a sum parameterized by graphs, the interesting thing is that more elementary than Kontsevich weights and so on thing appears, which is the use of Butcher series. So let me tell you just very quickly a couple of things. So Butcher series, it's a tool in the study of ODEs. For example, if you have a vector field in Rn and you think of its flow, where the time parameter is now formal, so you do a formal Taylor expansion of the flow. So Butcher, I mean, this formula was known from before, that you can express this as a sum parameterized by rooted trees. So this kind of rooted trees graphs. And what appears here is called elementary differentials. So there are derivatives of higher and higher order of the components of the vector field. And so Butcher noticed that if instead of doing the exact solution, the exact flow, you do a Runge-Kutta approximation, for example, then the formula is the same, only the coefficients are different. So this gave rise to this theory of Butcher series, and there is a Hopf algebra of graphs behind it that also is connected to iterated integrals and renormalization and many things. So this is a very nice subject, in principle only connected to ODEs.
Can I ask a question?
Sure.
You say that this is the Butcher series is the one you get from the Runge-Kutta, or that the coefficients are different?
Yeah. Well, yeah, what I want to say is if you do the exact solution, then you get a very particular formula. If you do a Runge-Kutta, you get another coefficient. Yes.
And there is no relation, there is no control.
Well, yeah, there are very interesting relations that the set of all possible coefficients form a group. And when you refine the approximation, you are moving in this group towards the point that represents the exact solution. So this is a very rich theory that I'm not having time to say, but yes, it's not unrelated.
Okay, thank you.
May I ask a question too?
Yes, sure.
Yes, all right. So you said before symbol in the Kontsevich formula, you have bidifferential operators. So you mean principal symbols. So you just take the top derivatives.
Yeah, well, it's in a sense it's the full symbol, because you just apply. Let me clarify the symbol of P1, P2. If I up to some factors that I don't remember, it's e to the minus P1 minus P2 of the bidifferential operator applied to e P1x.
So you have full symbol in this case.
Yeah, full symbol. Yes.
All right.
Full symbol. Yes.
Okay. Thank you.
Thank you for the questions. So coming back, so there is this thing that in principle is disconnected to what I was saying, but if you recall this formula for the generating function, the analytic one, there were some Hamiltonian flows appearing there. So we can think that we can apply this formula to the Hamiltonian flows, and that's okay. Then we get a Butcher series, but it's expressed in terms of this map alpha pi, which also was dependent on pi, and it's non-trivial. And here a key ingredient is an earlier work that we had with Benoit Derain, that in which we found that this source map that was also defined by an integral, it's also a Butcher series. Not for this particular vector field, for another vector field, which again, it's our favorite by now differential equation that transforms infinitesimal arrows into finite arrows. This could be called Poisson spray in this context. Okay, then we have like a graph combinatoric problem to combine this Butcher series with this Butcher series that I didn't write, but it's the same type, only that instead of X is V. And you arrive to things like this. The black rooted tree corresponds to the X vector field, and the blue corresponds to the inner structure when you substitute alpha by the series. And then these circles are supposed to represent derivatives. So you get, by the Leibniz property, you get all sorts of mix. I mean, you could connect this to the first or this to the other one, and then you get a resulting graph. When you analyze that with some detail, you arrive to the fact that the graphs appearing in this particular way are exactly Kontsevich tree graphs like this. And not only the symbols, the Kontsevich symbols also arise in a very particular way from the combination of the Butcher series of the elementary differentials. And there is even more, the Kontsevich weights that appear for the trees, they can be related to certain numbers that appear from the point of view of iterated integrals. So, okay, I hope that the idea is more or less clear. So I come back to this, that from this Poisson geometric perspective and using Taylor expansion, we can understand pretty accurately the structure of this generating function, the formal one, and also this graph structure. So now the final result in the map is like this, is connecting these Poisson geometric constructions to the field theory perspective. And now we will switch gears. Instead of thinking of formal power series and graphs and so on, we will be thinking of maps, which are fields in that context. So maps from the disk into the Poisson manifold and so on. A particular set of PDEs for those maps, and a functional that takes maps and gives you a number. And combining all those ingredients, we will get a new perspective on the constructions that we got here, and also on the connections to the other things. So let me, okay. Again, in this part, the object of study will be a set of PDEs. So what I want to do now is to motivate where the appearance of these PDEs. And also, it also helps connect with what we have done before. So let's say that we have a coordinate Poisson manifold. And remember, there was this key relation let's say it could hold in general, but now we want to substitute this star product by Kontsevich star product. And we also want to use Cattaneo and Felder's work, which gives a formula for it in terms of field theory. So as an integral over certain possible fields, of an expression like this that I will outline now in a second. So in this formula, I want to highlight two things. The first is that this X, big X and eta, big X is a map from a disk into M. Here is the disk. Eta, it's a one form on the disk with values on the dual vector space. That is the coordinates M. Another ingredient is that there are 3 marked points in this disk, in the boundary, and they appear here. So you are supposed to evaluate this map on those points, and evaluate F on the first, F2 on the second, and this is a delta which says that the value of this field at that point should be little x. Another very important ingredient is here in the exponent is the Poisson sigma model action that was discovered by Ikeda and Schaller and Strobel. It has this formula in terms of this. So it's a functional. It takes these maps and gives you a number. So let me hand wave the next step without writing formulas, although they are very simple heuristic manipulations. What I want to do is to take this integral seriously as if it was a finite dimensional integral, which is of oscillatory type, right? When h goes to 0, this is a fast oscillating term. And in principle, I could evaluate it using stationary phase. And if you think formally of that, then there would be a relation between this functional and this contribution, right? If you remember stationary phase formula, that's how it works. But actually, we have to be a bit more careful because it's not any two functions that I put here. There are these exponential functions that are familiar from Fourier transform. So they also contribute to the oscillatory exponent. And not only that, but this delta here, I also want to do a Fourier transform of it and express it as the Fourier transform of also an oscillatory thing. So the result of all those considerations leads you to a certain exponent here, which is this one that I just wrote. It's the Poisson sigma model action plus these linear terms on the p's. Here delta, instead of writing x evaluating at z1, I write the delta distribution on the disk evaluated on this map and so on. I call this the modified Poisson sigma model, I think. Okay, and so as I was saying, if you take this as an oscillatory integral, then you are naturally led to the conclusion that this guy is defined by the critical points of this guy. These are heuristic considerations because this is an infinite dimensional integral, but suppose that this was the case, that this works like that, and then we are led to the idea of understanding critical points of this function. So at this point, we can forget about the heuristics and say, okay, this is a sound functional, and this is a sound set of PDEs for these two maps, X and eta. I want to say, I don't pretend for you to, I wrote it just to say that it's very explicit. And what I want to highlight about this system is, well, first that the unknowns.
Can you solve it in particular cases?
Yes, I'm going to mention this in a second. Yes. Actually, the theorem says that we can solve it in all cases.
But so, I mean, can you give explicit resolution?
Sorry?
Can you give explicit formula in some particular cases?
Yes.
And then you can go back as much. I mean, can you realize any vector series with this?
Yes.
Okay.
We can connect the whole thing and relate it to the first thing. But Yes, this will come in just a second.
Thank you.
So the unknowns in this system are the map X, the one forms eta, and this parameter P3. These are unknowns. And then the P1, P2, and X, they enter as parameters in this system. I think of them as being fixed. For example, this little x appears here as providing the value of x at 3, and P1 and P2 appear here multiplying these deltas. So these are parameters in the system. I denote it like this. There's a system that depends on pi and on this parameter. And one more maybe technical remark is that, as Eva was suggesting, when you look at particular cases, for example, even when pi equals 0, and you look at the solution, you find, or some solution, because this is underdetermined. I think this will be clear in a second, but there are many solutions. In any case, all the solutions in that pi equals 0 case are discontinuous at these marked points. So what does it mean to evaluate this distribution in a discontinuous function? And then we extend the distribution to discontinuous maps in this particular way. I mention it just because, not because of the formula, but because this particular choice of extension is part of the information here. Okay, so now we have the ingredients to tell you what the main result is. So here are the hypotheses. We have a coordinate Poisson manifold, and associated to it, we have this Karasev integration and this particular generating function given by the formula. So first of all, what Eva was asking, families of solution always exist. And the germs of such a solution are classified by certain triangles that I want to mention in a second. But what I want to say is that geometrically, it's a constructive proof. So we show that every solution of that system corresponds to a very particular geometric object, which I call G triangle. This word families means that not only you have a solution for one choice of parameters, but you have a family of solutions smoothly depending on the parameters for small parameters, so in a neighborhood of 0. So what I keep of this first part is that, yeah, solutions exist, and even more, we can say what they are. But the important thing is that if you have such a family, you can plug it into the functional and get a number. But this number will depend on the parameters of the PDEs, right? So this defines a function of the parameters. And the key point is that this function of the parameters that comes from the functional perspective is exactly the same as this canonical one that we had before. So one can interpret this result as saying that actually this can be interpreted from a functional perspective, evaluating this functional on this particular set of solutions and so on. Okay, so I'm almost finishing. I just want to mention a couple of details related to these triangles, which I think, in a sense, is my favorite part of all this, because it clarified some things that to me I didn't understand about the Poisson signal model. So probably for other people were more clear. But in any case, now we have a very, very rigorous idea of what is going on in this semi-classical level. So this is the disk. And let me tell you first, what I'm going to do is think of the case where pi is constant. So what happens, one can write explicitly the solution in that case. And what happens is this, let's just first think of the map X. that mapped this disk into Rn. In this explicit solution, you see that, well, these are actually punctures. So these points are not in the domain of X. And this arc in the boundary connecting this puncture to this puncture all the arc goes to a single point. The other arc goes to another single point, and the arc below goes to another single point. More interestingly, if you take a path like this that goes from this component of the boundary minus these insertions to the other, this would be a path, it mapped to a path like this, right? It goes, let's say if it was like this, it goes like this. And here comes a more analytic estimate. If you take this to be an arc of a circle centered at this with radius epsilon, then as epsilon goes to 0, this path tends to be an edge of the triangle. And the same happens with circles around this and this. So what is going on in this pi constant case is that the disk is secretly just a singular parametrization of the triangle. So I repeat, the interior of the disk goes to the interior of the Euclidean triangle. And the delta terms in the PDE specify exactly how you approach the edges, but it's only in a limit. They don't belong to the map, to the domain of the map. So again, it's not, the maps are not singular geometrically. It's only that the parametrization is singular. It's a singular way of parametrizing a triangle. And what happens for, let's say, arbitrary pi, I mean, a bit remarkably, is that this picture generalizes, not only in the map X, but when you combine X and eta, and you think of it as a singular family of cotangent homotopes, for those who know. But in any case, what I want to say without detail is that this picture generalizes, and now this triangle actually lives on this Karasev groupoid, on a particular source fiber of it. The edges are not straight lines in the Euclidean sense, but they are the groupoid analog of that, meaning that this line is given by a right invariant flow, for example, generated by P1, and this one is a right invariant flow generated by P2, and so on. So there is a Lie-theoretic triangle living inside here, and the solution is secretly just this triangle. Okay, so let me just say two things. I mentioned that the system of PDEs was underdetermined, and in this geometric picture is very clear what is the ambiguity. So the edges are fixed, but the way of the filling is completely arbitrary, as long as it's smooth. You could, whatever, in the middle of this, put a deformation of the interior of the triangle, and it will be just as good as a solution as before. From the field theoretic point of view, you can interpret this ambiguity in the filling as different choices of gauge fixing. And in the first case, when I was referring to the pi constant one, I was choosing the familiar gauge fixing from Poisson sigma model, like this, uses the Hodge star. And the next thing that I want to mention is that in the context of conceived star product and the idea that it's associative, it's very familiar to see this kind of drawing in which one imagines one single disk that it's getting pinched like this into a union, a union of two disks glued at a point. And you could do this in two different ways, and this is what is behind the associativity relation. At least in the semi-classical level that we are discussing here, the picture is much more transparent from a Lie theoretic point of view, because gluing two disks along a point corresponds via this picture to gluing two triangles along edges. So in particular, if you want to check that this local groupoid is associative, you get the standard simplicial picture in which you glue triangles into a tetrahedron, and the fact that you can feel it allows you to prove associativity. So this is something that I find interesting. And it's not only heuristic, so we have a concrete system of PDEs and you can show everything with big detail. Okay, so this ends the main part. So in the 4 minutes that I have, I just want to make three final comments. The first comment, it's about what happens to other conceived graphs. I talked about the trees, but what happens with the loop graphs? And so a PhD student that is working with me, Gabriel Ledesma, is working on the following, that the Lagrangian given by the graph of multiplication, from the Lie theoretic point of view, it can be enhanced with a half density. And this goes along the, for example, in semi-classical analysis, the enhanced symplectic category that Guillemin and Stenberg, for example, have in one of their books. And what happens is that the one loop diagrams correspond to this enhancement. So it's a half density that satisfies an associativity equation. So this one loop part, it's also can be digested from the Lie theoretic point of view or the geometric point of view if you want. But a big question is, what about the whole thing, the whole quantization? Can you actually, using some implicit analytic methods, produce such a quantization and recover, for example, Koncevich's formula by a Taylor expansion? I think, well, without much justification, I think the answer is yes, but there is a key idea missing so far. And I think these considerations that I was just saying about the Poisson sigma model, I think they could help into having this further idea for such a construction. And the last thing I'm going to mention, it's an ongoing project with Rui Fernandez. It's about integrability. So, so far I was only using local groupoids, but I also mentioned that there might be a problem of extending these local groupoids to a global groupoid. So what's the role of that integrability property with respect to quantization? And it seems that it has to do with non-formal star products. So for a very particular and flexible class of non-formal star products, we can link the integrability property of the underlying Poisson manifold to associativity. So if someone asks further, I will give further detail. But so far, I leave you with this vague idea that integrability does enter, and apparently it enters for non-formal quantizations. Okay, so I think that's all. Thank you for listening.
Thanks a lot for your talk. Let's thank. So if you have questions, I don't see any particular question here on the chat. Brent has a question. Brett, go ahead.
Hi, Ale. Thanks for your talk. I'm going
Hi,
to
Brent.
debate and ask about this final result about the non-formal star product. So could you
Yes.
explain a little bit more how to link these things, please?
This part.
The very last thing you mentioned. Yeah.
Yes. Okay. Thank you for the question. Well, there are particular examples, for example, Moyal product and quantizations of the linear Poisson, in which you can provide integral formulas for the star product, and then it's not only a formal family, but it's a family for age varying from 0 to 1. But in particular, in the linear Poisson case, you see that the structure that you get is naturally not an algebra, not a family of algebra, but a family of what is called partial algebra. So when you want to do F1 product F2, it might not be defined unless these two functions satisfy some smallness condition. You can think of, in particular, the Fourier transforms have to satisfy certain smallness in their support. And what I want to say is that algebraically, once you have such a partial algebra, that you can imagine that is the analog of a local groupoid. Even when the arrows are composable, you might not be able to multiply them, right? Because they are not small enough. Then associativity of three things does not imply associativity of more things. Because, just because the product is not defined for all objects. But what I mean by complete associativity, it means that whenever there is a way of associating these things that is defined, it always gives the same result. You see, if you come and associate this in a different way, which is also defined, we want these two things to be equal. This turns out to be an independent condition. You could speak of n associativity when there are n objects here. And so the more concretely, now that I have introduced this thing, is that if the star product, which is a partial algebra, is n associative for all n, then the underlying Poisson manifold has to be integrable. That's the concrete result.
Nice.
Well, it's maybe in progress, right?
And does it play a role, the equations that you described you described very particular equations that are connected really to the flow of the Hamiltonian vector field. So this is how you relate to the integrability, or not?
No, the connection to integrability is a bit more elliptic. It has to do with this work of Rui Fernandez and Michaelis that I mentioned, in which they understood integrability also in terms of this kind of different ways of associating, but not now functions in this algebra, but element arrows in the local groupoid.
Okay. Very nice.
So you have n arrows, you can associate it in different ways, and you want different ways to be equal, and they showed that this condition is equivalent to integrability. So yeah, it's a bit more complicated.
Okay. Nice. We have a question by Ivan.
Hi, Alejandro. Thank you.
Hi.
Thank you for the talk. I just have a quick question about this modified action of the Poisson sigma model. So if we don't modify the action, then we can do reduction, and then we come up with the symplectic groupoid that integrates a Poisson manifold.
Yeah.
I was curious if there is a way to recover the local symplectic groupoid by some version of reduction. So if there is some geometric interpretation of the
well, one has to be careful about that, because you see, this is on the disk. What you're referring to is when you, instead of a disk, you take a strip and you do the Hamiltonian formalism, which is something actually very different from this disk with insertions. So the connection between this thing that you're mentioning, that actually I should have also mentioned, with this thing that it's the actual setting for the Kontsevich star product, it's a bit more complicated. The idea is that these strips, where you can think that the vertical directions are giving you the groupoid arrows, they sit here in a funny way like this.
Mm-hmm.
So yeah, it's not so, I mean, you can relate the two things, but I would say that this is richer.
Mm-hmm.
And the fact that these insertions here, they are very fundamental. If you put this to 0, then you don't get, you get just the trivial solution.
Mm-hmm. Yeah, I think that was kind of my question is, yeah, like how you relate with boundary conditions. Like you could have chosen different boundary conditions for for example, the strip, and getting somehow a different answer. But I think this clarifies. Okay, thank you.
Okay, thank you for the question.
I have a question. Yeah.
Okay.
Yes.
Yeah. Oh, it's hi. So it's rather a historical remark. So for the case of a linear Poisson structure, which corresponds to Lie algebra and Lie group,
Yes.
Berezin in I think 1969 or 67 perhaps, just wrote down this integral formula for the star product. So
yes,
it was a paper in functional analysis, first issue of functional analysis and its representation. So it is very famous issue of the journal, where there's Arnold's paper about Maslov class and so on.
Yes, thank you. Yes.
Yes.
I should also have mentioned that many things were inspired by the book of Karasev and Maslov, where they also investigate some of these things. So yes, thank you.
Yeah.
Yeah, I have a question.
Yes.
Hi, Alejandro.
Hi.
So this is back to the last page, where kind of a converse of Brent's question. Clearly, the global integrability is not sufficient for complete associativity. At least probably not. I mean, there are examples like like Riefeld's theorem about no good global quantization of the two-sphere. But I wonder if there's some assumption on the integrability, that is to say, some assumption on the symplectic groupoid, which would imply that some kind of a non-formal quantization.
Yeah, a great point. You see, the way to relate this, the way how this works is like this. If you think of this kind of expression, suppose that there is an integral expression for it, and then you do stationary phase approximation. In the leading term of that stationary phase approximation here would be the groupoid associators. So that's why it's necessary, but as you said, it's not sufficient. So trying to answer your question, I would imagine that a property that would ensure that it's also enough would have to do, well, it would, in terms of the quantum product, I would say that it would have to do with properties that allow you to conclude that the stationary phase approximation is exact, or things like this, or that the extra terms are under control. I have in mind one of your papers where one thinks of geodesic triangles, right? Yeah, and yes, in that case, which is symplectic, I think that would be an instance in which you could do what you were saying and conclude that it's also sufficient. But yeah, I think in general might be a hard question to to have control over the other terms, unless the star product has some very special properties.
Okay, thanks.
Thank you.
Okay. I don't see anyone else raising the hand. I'm going to ask the people connected on YouTube. Now 6 people connected on YouTube. You can type your questions if you want. I'm gonna read them.
Of course, yeah.
No questions. I mean, there are like 6 likes in YouTube. That's quite good. There were 10 people connected, but no questions from YouTube. So I think that's all, unless there's somebody else who wants to ask a question.
Can I ask a question, Eva?
Yeah, Rick, go ahead.
Yeah, I was wondering if you ever thought about allowing in this disk for topology. So instead of being a boundary of a half disk, being the boundary of a surface.
Yes, that's a good point. I haven't thought about it, and in my, I mean, from the Poisson geometry perspective, I know from you actually, and Ivan, that you would expect certain Abelianizations and things like this, but I was thinking about your question in the context of field theory. I don't know what to expect. So just to draw something, instead of being a plain disk here, you have a surface, for example. I don't know, maybe, yeah, I haven't thought about this. It would be nice to understand the semi-classical solutions in this case as well, for sure. But yes, maybe this picture that I just drew, if you repeat this inside this, you will have something similar. Okay, yeah, sorry, I don't know how to answer.
So, sorry, if I may make a micro comment. So I think if you consider the torus, for example, in field theory,
yes,
you recover something that looks like the super trace, somehow like the Euler characteristic.
Right.
So I would imagine that doing this kind of path integral approach for surfaces with higher genus, you may want to get something that at least at genus 1 looks like the Euler characteristic, for example.
Yes, yeah, thank you. That's a good point. So now you would remove a little disk and put these 3 insertions there. Yes.
Mm-hmm. Yeah. Mm-hmm.
Nice. More comments, questions? You have a dog, Alejandro, there, right? At home?
I have a dog. Oh, everybody asks me. No, it's a neighbor's dog. It's just that the barking seems to have a frequency that goes straight into the microphone. So it looks like as if the dog was next to me, but no, I don't have a dog.
Okay. Thanks a lot for this very nice talk on this kind of stationary solutions ideas applied to this whole new world. Thank you very much. Let's thank Alejandro again. We go on with Pavel Severa, more quantization. Don't miss it. Quantization of Poisson-Hopf algebras and moduli of flat connections. So see you next week on Thursday. Bye-bye.
Bye-bye, everyone.
Bye.
Bye.